Hello, my name is Walter, and I'll be talking about rapid spacecraft payload development in the context of a software experiment that flew over the course of this past year. You'll see lots of names here, and that's because I had a lot of help, particularly from Caleb Adams, Sergey Gridney, and Nick Kramer at NASA Ames Research Center, Alison Lund, Eric Brune, Oscar Flordel, and Frederick Brune at UNIBAP, as well as my advisor, Dr. Alan George, at the University of Pittsburgh. I'm a graduate student in the NSF Center for Space, High Performance and Resilient Computing, or SHREC, at the University of Pittsburgh. And let's get started. So broadly, I'm going to spin this presentation talking about a software payload that we all developed, and the motivations around that work, which I feel were kind of unique. And then I will try to use that to frame this broad observation, and that's that high-level software abstractions and fault-tolerant high-performance hardware and lots of shared reuse, multi-mission, multi-purpose spacecraft are fundamentally giving a lot of new meanings for what flight software is and can be. So the Distributed Spacecraft Autonomy Group, where this payload was conceived and developed initially, the Distributed Spacecraft Autonomy Group at NASA Ames Research Center is a project that's focused on developing and demonstrating technology for swarm interaction, autonomous coordination, and so on and so forth. That's culminating in two primary demonstrations of that technology development. A flight experiment slated to fly on the Starling 1 spacecraft. That's four 6U CubeSats flying in formation, as well as the Lunar Position, Navigation, and Time simulated experiment, which looks at providing those services using an autonomous cluster of up to 100 spacecraft. So as part of the DSA project, one of the things we put together was something called the Swarm Test Framework. It comes in a variety of configurations, but one of the earliest ones was the container-based one. And basically it lets us test multiple instances of the flight software in super early versions of development through containers at near native performance. It's a low-cost approach in terms of effort. It gives us a fairly modest amount of simulation fidelity, but it's really good for early life cycle testing. Another product of the DSA project and a critical part of this experiment was the DSA COM app, which is a publish-subscribe interface for CFS that extends the software bus across a network. It uses the data distribution standardized specification for publish-subscribe communication. DSA wrote an app that sits on top of that, sits on top of the RTI Connect Micro library for DDS communication. There's other applications out there that work at kind of a similar level or kind of target a similar idea, but this is specifically a product of the DSA project. So on UNIBAP's side of things, the experiment ran on board the Space Cloud, which is both the hardware and the software, including the operating system and the interfaces on top of that. The hardware is a quad-core AMD CPU and GPU system on chip. The payload processing computer also includes an FPGA as well as an Intel Vision processing unit. The Space Cloud framework, which I'll refer to a lot, includes the operating system, which is an Ubuntu Linux derived distribution that basically runs payloads in the form of Docker containers. It uses remote procedure calls, or RPCs, as the way to communicate with the host system or sensors on board. So that picture is of the SCV-4 spacecraft, which the Space Cloud hardware computer, the IX5102, sits on board, and we had access to a hyperspectral imager as well. So this mission, the deorbit Dashing Through the Stars mission, hosted the experiment, still up in the air, still running payloads, and actually they are still uploading new experiments and running and deploying new payloads right now on board the ION SCV-4 spacecraft. So those are the background. So talking about our payload a little bit, this experiment was essentially a very opportunistic sort of expansion of the DSA project. We had a couple of thoughts floating around, like, well, how reusable is DSA COM? Because that was a tool that was conceived as part of this push for reusable swarm infrastructure, reusable technology for swarm communication and autonomous behavior. We also noticed that the Space Cloud framework was eerily similar, at least superficially, to the DSA swarm test framework. They're both container-based, right? So how different can they be? Talk about it. And we also, I was interested in fault tolerance and using containers as kind of the mechanism or the interface for applying sort of fault tolerance in a spacecraft setting, because replication in terrestrial settings where containers are most popular and kind of a lot of the original work came about in terrestrial computing, it's also for fault tolerance. Usually it means something different, but the question still kind of persists: can we benefit in the same way? So this started with a mission concept in September of 2021. Essentially, given the tools at our disposal and kind of the questions in our head, the first concept we came up with was to do some image processing on board with the image sensor, and applying redundancy with a very simple mechanism, triple modular redundancy. So we came up with this rough diagram of 4 different containers, one of which would handle the image communication, and then 3 of which would do the image processing, and then we added a voter to actually vote on the results of that. So that's the full loop. Primary container gets an image, secondaries perform processing, and then they return the result and we vote on it, and that's our experiment. So there's 3 new CFS apps that we developed for this. They're all very simple. I'll go through them pretty quickly. We liked this concept of operations, and it was September, and we actually didn't have very much time to put this together, so we ran with it. So we started with the code base that was in development for the DSA Starling mission, which is CFS-based flight software. We pruned out almost everything except for the Core Flight Executive and the DSA COM app that I mentioned before. We added the skeleton for our new apps, and we wanted to exercise the fault tolerance, but both the duration of the mission as well as the fact that the Space Cloud platform actually uses a lot of fault tolerant and fault masking under the hood to kind of prevent upsets from even being visible to users. So to make sure that we actually used the TMR, we intentionally sabotaged one of our 3 containers and had it report an incorrect result periodically, so that we could actually see, did we actually vote? Because if everything works and you see logs that saying, your image processing just, worked every time, it's not as fun. One of the reasons that we were able to prune out almost all of the apps was because the Space Cloud framework effectively handles a lot of what we cared about in terms of health and status, commanding and telemetry even. A lot of things that are inherent to most flight software systems, that was all delegated up to Space Cloud framework. So it dramatically simplified the design. I know that diagram I showed was very small, and there were details that weren't captured by that, but it wasn't too far off from the full picture. So the gRPC app, RPCs being remote procedure calls, this is the interface between the container and then the host system and any sensors. There's implementations for many languages. It's basically a language agnostic way of making remote function calls. And this is what Space Cloud Framework uses for communication outside of your container. So our implementation makes this function call to ask for an image every 10 seconds. We save it to a Docker volume, which I'll talk about a little bit more later. And then we announce that file using our publish subscribe network middleware. The TMR app, just as I said, we basically run our image processing application 3 times and vote on the output. This is definitely the simplest way to do it, and even in, especially in situations like terrestrial cloud computing, when you're trying to do fault tolerance, there's much more sophisticated ways to operate with regard to process failures on a lot of different levels. This is just our design. the image processing, which we called the CV app. I want to emphasize that the Space Cloud Framework has a lot of tools that are kind of ready to go for you. The vision processing unit, there's the GPU and all the libraries to interact with that. They have OpenCV ready to go. They also ship Python, Python interpreter in the Space Cloud Framework. And if you've been checking the date on the right side of your screen, it's October of 2021. We could be using the hardware to its fullest extent, but we wanted to try out image processing, and what is easier than from PIL import image? So we took the path of least resistance, and our image processing app, it just calls Python. We return the image entropy computed with some pretty common image processing libraries and feed that information back into the app. So Docker volumes, they are kind of a generic abstraction for persistent storage that Space Cloud Framework uses. And we use this to actually share the images across containers. So when the primary grabs an image, it actually saves it to that volume and announces its file system location over the virtual network. And each of the containers who are subscribed to that message see, oh, there's a new image here. They go and that triggers them to run their processing loop. They spit out the result, but they are able to read the image because they've all mounted that volume into the same space of their container. So it's sort of it's a networked file system, right? But it behaves like a locally mounted file system because it kind of is. So this was how we actually shared images around. All right. So it's November 2nd. We finished designing our apps. We make our final flight software change on November 16th. And then secretly, Unibap is doing amazing work behind the scenes. And November 29th, we finally get successful integration onto the spacecraft. Our payload's on there. They did actually have to upload some pieces of the software after we got into orbit, which is pretty cool. I can't speak to more details on that, but eventually we launched on January 13th on SpaceX Transporter 3. So that was all of the development, what we built, how we built it. Talking about our results, you might look at a high level of the sort of mission that we're talking about and the pieces of it and say, okay, well, are we assessing this mission architecture for long missions? No. We're not demonstrating fault tolerance over an existing design or doing an empirical measurement. Does this handle things better? We're not focused on the image processing techniques or looking at the hyperspectral imagery specifically. And we're not trying to specifically flex the hardware for everything that it's worth. This experiment was about empirically assessing the reusability of our flight software and kind of looking at this as almost a meta experiment of development. Doing tests as you fly, but kind of to a new extreme with a swarm test framework, and trying to look at the way conventional cloud computing is done and the way software is written on the ground, and kind of looking at how that compares to conventional flight software and other mission-specific designs. So, with that in mind, in June, we had the first run of our experiment in orbit. It didn't run on live image data, it was on a preloaded data set. And our voting app actually saw all the responses in agreement when it expected. Our intentionally sabotaged image processing container returned the wrong answer when we expected, and the voter correctly ignored the wrong answer. So not too many metrics to measure for success, but of the ones we had in mind, we were successful. And the full run took place on October 21st last year. Same as the first, but with actual image data and run live. So for each run, there were 2 of them for a minute apiece. We took 4 images and we saved, and we're actually got the data back down to verify on the ground as well. Our secondary container returned an error calculation when we expected, and the TMR setup did vote correctly even in the presence of an injected error. So here's a snippet of what those logs look like. At the top, we get an image, and then we get a response from 2 of the satellites, and then we get the wrong answer from the third. It says sat, but these are just the containers. but we vote for the answer that the first two actually responded one. This is a snippet from the TMR carrying container. So mission success. It worked. We flew in orbit. So what's the big deal? Well, the design from that first sketch, which is basically what you saw on that screen, until the rocket physically lifting off was 170 days. From the first commit until the last commit in our software repository, in our version control, that was 60 days, start to finish. And there was a lot of empty time in between. We got to use a lot of really user-friendly tools and environments. It was kind of a breeze. We really didn't have to fight with the tool chains that much. For the most part, we were able to just bring the tool chain we needed because of the container-based approach. You know, okay, well, we need this build environment. Okay, then use it. And that's what we did. There weren't any architectural differences between the machines that we tested on and what flew. I mean, they were both Intel, like AMD 64 processor architectures, basically identical because of the way containers work. Different kernel, which I'll mention a little bit more on that later, but it's otherwise kind of an identical system. So it really is test like you fly, but with no flat sats or hardware twins. And we didn't have to write any hardware drivers. Like I said, we used the RPC to actually get image data. We didn't have to fight a camera or like stick to a different driver. You know, it was very easy to work with. And the abstractions that we got to work with from the container side, the kind of cloud computing side of the technology stack, they're pretty intuitive. They're well defined. There's not too many details exposed, but that makes them really easy to work with. So we successfully actually used the DSA COM app in orbit, which is great. At least as of this presentation, it hasn't flown just yet in orbit, so that was great. We radically reused the test infrastructure. We basically used the Swarm test framework and changed the apps, and then, you know, run test, but we took the things that we built for the test and delivered that, and that was our actual flight product. And we kind of showcased DSA COM being this publish, subscribe extension across the network, being a way to write your applications in a way that scales to many many processes, whether that's local, whether that's multiple spacecraft. I mean, that's a fundamental building block. And it really, using the containers made isolation and redundancy from that perspective a breeze. It made forming a mission design and a flow of events a lot easier to reason about. You know, like I said, it was kind of an identical flight system when you compare the flight system for, you know, what we were testing against, the caveat being the Linux kernel. We did have to do a lot of extra work, and especially Unibap were very helpful helping us out. The networking middleware and specifically also the CFE task scheduling have some extra expectations that most containerized applications don't worry about or care about. We also, you know, I mentioned there's definitely room to do a lot more creative, more efficient things on the side of processing, on the side of redundancy, and maybe even doing load balancing. So on paper, this was still a fairly sophisticated final product. If you look at the whole thing, it was a multi-core, multi-threaded image processing deployment that actually embedded in itself some fault tolerance mechanism. We were running on live hyperspectral imagery data from low Earth orbit. And from our perspective, the app designers and developers, we did all this in 2 months, which is, I think it's pretty cool. In reality, the Space Cloud framework, you know, handled that complexity. It's not, you know, saying 2 months, it's like, you look at what we did, there was a lot more going on under the hood. But that was hidden to us. If you look at it from the perspective of we're the developers and you know, we have this mission idea, we need to implement it and get it running in space. It's 2 months was 2 months. That is how long it took. And it kind of mirrors what you would see in terrestrial computing. If you're building like a web application, if you got some idea for, you know, some application that does something kind of fun, that's like a social network extension or it's a bot or something, you can have hardware up and running in minutes. You don't have to spec out a bunch of machines and build them and configure them. This is what cloud computing is enabled, is this very, very rapid life cycle. And we saw that in our work on the space cloud. So, in conclusion, my argument here that I presented today, and I'm curious to know what you guys think, high-level software abstractions, fault-tolerant, high-performance hardware, and like massively multi-mission spacecraft fundamentally mean that flight software includes rapid development life cycles. It includes developer-friendly tools, reusable components, like seriously reusable components, iterative deployments, and you do edge processing at scale. I mean, think looking towards the future, not just one spacecraft running these containers, but many, and very useful generic abstractions, which all ultimately mean that we get a lot more done in space. Thanks for listening.